Hello! Have you ever wondered how to find the oxidation state for an organic molecule? This video will show you some quick tips on how to find the oxidation state and also how to know if a reaction is a redox reaction for organic molecules. So there's no doubt you've probably heard of redox reactions before. This is a topic from Gen Chem usually. It's a type of reaction where one of the species is oxidized and another is reduced. Let's quickly review what you probably learned from Gen Chem. The first way that we can define oxidation and reduction is based on the electrons. So this may be, you may have learned some sort of acronym like oil rig, or you may have learned Leo the lion says grr is another one. Basically, this has to do with gaining and losing electrons. So for this definition, we would say that oxidation is losing electrons and that a reduction is gaining electrons. That's the most common way to talk about oxidation and reduction in Gen Chem terms. However, you may have heard other ways that you can figure out if something is oxidation or reduction. There are some textbooks, including some biology textbooks, which define oxidation and reduction in a more simple way that works for only some systems. First, if you're changing the bonding to an oxygen with a certain element, you can look at it in terms of that. So for example, oxidation would be you're gaining bonds to oxygen or you're actually adding oxygens to the molecule. Reduction would be losing bonds to oxygen for the atom or you're losing oxygen overall in the molecule. In a similar way, you can look at what's bonded to hydrogen. So oxidation would be losing bonds to hydrogen, whereas reduction would be gaining bonds to hydrogen. So this goes to show that we have some strategies already. However, we really want to find a way that always works and that is specific to organic molecules. So without further ado, let's figure out how we're going to do that. Generally, for this type of problem, you would have a full reaction, but I'm just going to use the molecule on the right to demonstrate some of the topics, and then we'll do some examples. So the first thing we're going to do is we're going to look for the atom that's changing from the starting material to the product. So like I said, we'll have full examples in a minute, but for right now, let's just say it's going to be this atom here, this carbon with the double bond O. 90% of the time, since you're in an organic class, you're going to be looking at carbon, but there are other examples that you could look at. So the next thing we're going to do is to see what's attached to the atom we're looking at, and then determine the oxidation state based on the electronegativities. So if you look here, it says if the electronegativity of the thing attached to the atom is greater than the electronegativity of that atom, for example, carbon in this case, then we're going to give it a +1. If the electronegativity of the attached thing is less than the electronegativity of the key atom, which is the carbon, that means -1. And then if there's an electronegativity that's equal, for example, if it's the same element, then that means it's going to be 0. So let's look at the example to the right. So this carbon, again, is what we're looking at. So we're comparing the electronegativity to carbon. How are we going to know the electronegativity of an atom? Right, we're going to use the periodic table. So we know that the most electronegative atom is fluorine. So that helps me remember that electronegativity increases going from left to right and also increases going from bottom to top. So the closer I get to fluorine, the more electronegative things are in general. All right, so let's look at the example. So if we look at the carbon going up, we've got an oxygen. So is oxygen more or less electronegative than carbon? Right, it's more electronegative. So what number do we want to add to this part? We're going to say +1, right? Because it's more electronegative, meaning the carbon's going to be more positive. That's why plus. Now, one thing we do need to consider is we've got a double bond. So when you have a double bond, it basically, for oxidation state, counts twice because it's bonded to oxygen twice. So instead of being +1, actually this total is going to be +2 because of the double bond. All right, so next we're going to look at the left side. So that's a carbon, right? So because it's a carbon, is that electronegativity going to be the same or equal to the carbon in the middle? Right, that's a trick question because it's going to be the same. Because they're the same, that means we're going to put a 0 over here. And then the last one is hydrogen. Now, hydrogen's a little bit tricky because the actual electronegativity is hard to determine because it kind of shows up in two places, periodic table based on its behavior. And the electronegativity values, if you were to look them up on a table, are actually pretty close for carbon and hydrogen as well. So for this case, we're always going to consider hydrogen to be a -1. So anytime you see hydrogen, just assume it's going to be a -1. You don't have to look up the numbers or anything like that. It's just one of the ones you'll want to remember, okay? And that'll make it work out. All right, great. So then we're going to have +2, 0, -1. And then now we'll go to the next step. So the next step is easy. We're just going to add the groups together to get the oxidation state for that particular atom. All right, so for this one, it would be 0 plus 2 minus 1. So the oxidation state for this particular carbon would be plus 1. And you do want to make sure you put that plus, don't just leave it as a 1. So I may be able to stop there, but if I have a reaction, I'm going to want to determine what kind of reaction it is based on the oxidation states. So of course I would have another product that I would have done the same process with, adding up the things and getting the oxidation state, and then I'm going to compare them to figure out what kind of reaction it is. So as you can see here, it says if the oxidation state increases from the starting material to the product, so like if this is 0 and the other one was 1, for example, then that would be an oxidation reaction. If the oxidation state decreases from the starting material to the product, that would mean that you have a reduction. So if it went from 0 to say -1 or -2, then that would be a reduction reaction. Then the last option is it doesn't change. So if the oxidation state stays the same from the starting material to the product, that means that there's no change. It's not an oxidation or a reduction reaction, it's some other kind of reaction. So with this strategy in hand, let's do some examples. So for the first example here, you can see that we're actually going to have to figure out what is the part that's changing. So I probably want to map the carbons. So if I put the numbers on the carbons over here, what will be the matching numbers over here? Right, that carbonyl is going to be number 3. So then if I put that there and have all the same numbers, which atom is changing? It's carbon 3, right? So that's the one I'm going to use. So I'm going to erase the mapping now. And that's what I'm going to calculate. So now I want to find what's attached to the first thing on the starting material, right? So for this carbon, I've got 1 oxygen, so that's going to be +1 for carbon. I've got 1 carbon, so that's going to be 0. And I have how many hydrogens? 2, right? So that's going to be -2 total for the 2 hydrogens, right? Then on the right side, if I do the same thing on this oxygen, I've got a carbon again, so that's going to be 0. I've got an OH on the right side, so that's going to be what? +1, right? And then I've got a double bond O going up. So what would that be? +2, right? So now this is a good time to have a reminder that we're not showing every single thing that's attached to this whole molecule. We're only talking about things directly that are connected to that one carbon that we're looking at, the pink carbon in this case, okay? So don't go down the whole molecule, just write on that one carbon what's attached. So now let's do step 3 and we'll add these together to get the oxidation states. So we should get -1 on the left side and +3 on the right side. So make sure that's what you get, and then we can move on. All right, so then the last thing we're going to do is determine the type of reaction. So this type of reaction is going from -1 to +3. So is that increasing or decreasing the number? It's increasing, right? So that means this is going to be an oxidation. Great. All right, so that one's done. So let's do the next one. So for the next one, we'll go ahead and map the carbons, right? So this would be 1, 2, 3, 4. And then over here is going to be 1, 2, 3, 4, right there in order. In this one, what atom is changing? Technically, it's 2 atoms, right? Both of the carbons on the double bond are changing. We only want to look at one at a time, so we'll just do that. So generally, if there's any question, I'll like draw an arrow to which one. But in this case, they're both the same, so it's going to give us the same answer, all right? So let's just highlight this one. Okay. So let's go ahead and draw the hydrogens in and then calculate what you think it's going to be. Pause the video and then come back and check it. All right, so first, are these the hydrogens you drew in? If not, make sure you go fix that and pause the video again. If that is what you got, let's continue. So are these the numbers that you got for the oxidation state? Right, so the one on the left would be 0 plus 0 and -1 for the 1 hydrogen, so that's -1. And then the one on the right would be 0 plus 0 minus 2 because there's 2 hydrogens, right? So hopefully those are the ones you got. And then now let's look at what kind of reaction this is. So we're going from -1 to -2. So that number is going down, right? So what kind of reaction is that? Right, it's reduction. So that's a reduction. All right, so hopefully you're getting the hang of it. So number 3, I want you to try to map the carbons yourself. So draw numbers on it, figure out where stuff is, and figure out which carbons are the ones that are changing. Okay? Okay, is this what you got? 1, 2, 3, that one there? Perfect. All right, so now that we do that, calculate the numbers and then come back and check the oxidation state. So pause the video again, do that. All right, is this what you got? Perfect. So remember, anytime you have a multiple bond, you're adding more of the same number, right? So that's why the triple bond is going to be +3. Perfect. All right, so then what kind of reaction is this? This is a no change, right? Because it's going from +3 to +3. So that'd be an example of a no change reaction. And it's totally changing elements. It is changing. It's just not an oxidation or reduction is what that means. All right, great. So now that you're hopefully getting the hang of it, you know the strategy, hopefully you'll be able to use this for any organic molecule that you see. You'll be able to calculate the oxidation states of the different carbons. And you'll also be able to recognize if something's oxidation and reduction more easily. And that's all we have for this topic. You're completely done. So hopefully that made sense. Make sure that you practice it to see if it works so you can find examples in your book, or you can, of course, always check Blackboard for activities for Dr. Cossey. Hope this helps, and I hope you have a fantastic day. Bye.